Hello everyone. In this presentation, I will explain how matrix additions become faster and more efficient using modern GPU architecture. Normally, matrix operations take more time on a CPU because they are processed one step at a time, but GPUs can perform thousands of operations at the same time, which makes them perfect for tasks like matrix addition. We use feature called unified memory, which allows both the CPU and the GPU to share the same memory space. This means we don't need to manually copy data between them, reducing memory overhead and improving performance. Using parallel computing, each GPU threads handles one part of the matrix, so the entire addition happens much faster. Overall, unified memory and GPU parallelisms together make matrix operations simpler, faster and more efficient. Okay, we have moved to second slide. What is matrix addition? Matrix addition is one of the most basic and important operation in the linear algebra. It simply means adding two matrices that have the same number of rows and columns. We add them elements by elements. For example, if we take the value at position I, j in the matrix A and add it to the value at the same position in the matrix B, we get the result in matrix C. So the formula becomes C of I, j equal to A of I, j plus B of I, j. Even though this looks simple, matrix addition is usually everywhere in scientific simulations, image processing and especially in machine learning where large matrices are processed continuously. Understanding this basic operation helps us see why splitting it up with GPUs is so important. Now we can move to slide 3. Understanding unified memory. Unified memory is a feature that makes GPU programming much easier and more efficient. Normally, data has been manually copied from the CPU memory to the GPU memory before running a program. But with the unified memory, both CPU and GPU share a single address space. This means the same data can be accessed from both sides without extra copy. Another big advantage is automatic migration. The system itself moves the data between the CPU and the GPU as needed during execution, so we don't have to manage it manually. Finally, this simplifies program. Developers can write cleaner and shorter code because they don't need to worry about memory transfer. This reduces the complexity and prevents many common errors. Overall, unified memory saves time, reduces mistakes and improves performance in GPU applications. Move to slide 4. Why unified memories matter? Unified memory is important because it solves many problems found in traditional GPU programming. Normally, developers need to manually allocate memory on the CPU and the GPU, copy data back and forth, and carefully synchronize everything. This process is time consuming and can easily lead to errors. Unified memory completely changes this workflow. It automatically manages memories and eliminates the need for manual data transfer. Developers can focus more on the logic of the program instead of worrying about where the data is stored. Even with this simplicity, unified memory still maintains strong performance. This makes GPU programming faster, easier and much more efficient. Now we can move to slide 5. Implementation advantages. In this slide, we look at the practical advantage of using unified memory in real GPU programs. First, it reduces code complexity. We no longer need functions like CUDA malloc, CUDA memory copy or manual synchronization, which usually makes GPU code long and difficult to manage. Next, unified memory allows faster development. Since the program does not have to spend time handling memory transfer, they can focus more on designing and improving the algorithm itself. It also makes debugging much easier because there is a single memory space. Tracking where the data is stored and finding error becomes simpler. Finally, unified memory improves scalability. The same code can automatically adapt to different GPU architecture and memory configuration, give better flexibility and performance across devices. Now slide 6. Performance characteristic. In this slide, we highlight how unified memory improves overall performance and productivity. First, unified memory provides almost 2x faster development speed. This is because developers spend less time dealing with manual memory operations and can prototype ideas much more quickly than with the traditional CUDA programming. Next, there is about 95% reduction in code size for memory related tasks since we don't need long boilerplate code for allocating, copying, freezing memory. Our programs become cleaner, shorter and easier to maintain. Finally, unified memory requires zero manual data transfer. We no longer use explicit CUDA memory copy calls because the system handles data movement automatically. This simplifies the workflow and reduces the chance of mistakes. Overall, this performance characteristics show how unified memory speeds up development while keeping the code efficient and easy to work with. Real world applications. Unified memory and fast matrix operations are extremely useful in many real world applications. One major area is deep learning. Training neural networks involve adding and multiplying huge matrices across many layers. Unified memory helps speed this process up and reduce coding complexity. Another important area is scientific computing. Fields like physical simulation, climate modeling, and computational chemistry use very large data sets and complex calculations. GPU oscillations with unified memory makes these operations faster and easier to manage. Unified memory is also valuable in financial analytics. Tasks like portfolio optimization, risk assessments, and predicting market behavior rely on large scale matrix computations. With GPUs, this computation can be completely much more quickly. Overall, unified memory helps improve performance and reduce coding effort across all these areas. Now we can move to final slide. Key takeaways. In this slide, let's summarize the key points from the presentation. First, unified memory grandly simplifies GPU programming. It removes the need for manual memory handling and reduces complex code. Second, automatic data migration means no longer worry about copying data between the CPU and the GPU. This improves both performance and coding efficiency. Matrix addition is the perfect example because it is used parallel element-wise operations, allowing us to fully benefit from GPU acceleration. Finally, unified memory gives us the best of both worlds. High performance with cleaner, more maintainable code. We achieve faster development, easier debugging and strong execution speed, all with much less efforts. And thank you all for listening to my presentations. I hope this session helped you to understand how unified memory and GPU oscillation make matrix operation faster, simpler and more efficient. If you have any questions or would you like to know more, I will be happy to discuss them. Thank you once again.